So this is about quasars, and this is the Google definition. If you put in quasars into Google, this is what you get. A massive and extremely remote celestial object emitting exceptionally large amounts of energy, which typically has a star-like image in a telescope. Blah, blah, blah. Huge. So that's the Google dictionary definition. I put the date on it because someday, hopefully, it'll change. Okay, so let's a bit of history. Quasars were first observed in the 1960s. Through a telescope, they appear to be stars, but they exhibit strange features not shared by ordinary stars. They have spectra which appear hugely redshifted, and they vary irregularly with timescales that range from hours to months. Early in the study of quasars, a huge heated controversy raged about the redshifts. Are they cosmological due to the expansion of the universe, or are they gravitational due to the near presence of a massive object, e.g. a black hole? Let me get the mouse out of the way. Cosmological explanation implies that quasars with large redshifts are extremely distant objects with truly phenomenal power outputs. They're very hard to explain. By contrast, the gravitational explanation allows the possibilities that they are modest-sized objects, not too distant, and with an easily modeled power output. As can be seen from the Google definition, the cosmological explanation is the currently accepted one. This is despite some incontrovertible, let's get this out of the way of the movie, some incontrovertible evidence in the form of observation of Alpha arc and alphas. The quasars are often associated with galaxies, with the redshift of the quasars significantly higher than that for the associated galaxies. So here's a striking example. It's NGC 7603 and the surrounding field. So I've got the next slide, I've zoomed in on it. So this is it. The NGC 7603 and a companion galaxy, NGC 7603b, which is called Object 1 here. The important thing is two little objects, Objects 2 and 3. And here's the bottom half blown up. So you can see the galaxy, a companion galaxy. There's a filament of gas joining them. And bang slap in the middle of this filament, there are these two strange objects. And when you look at the redshift, see, we've got the redshift for objects for the galaxy here, the 0.03 and 0.06 for these two. So they're not terribly far away, and they're not going apart very fast. But the redshifts for the two little objects, which are presumably quasars, are much bigger. So 0.3, we're talking about a third of Z equals 1 is about 1/6 of the diameter of the universe. So 0.3 is about something, or some proportion of the universe. So if this redshift is due to this guy being at that cosmological distance, it's miles, it's hugely behind here. And the chance of it appearing here like this is so remote that you can discard it. So these two objects, these two quasars, because that's what they are, have redshifts which are about 0.3, well, about 0.36 and about 0.129 or 19 or something. Different from the, presumably the cosmological redshift, presumably the filament, which is a fairly lightweight thing and won't have much gravity affecting it. Z.03 is probably pretty much correct. Okay, so here's what's written underneath where I got it from. So this example contains two arc quasars, objects 2 and 3, strongly associated with the galaxy and companion of lower redshift. And then there's some detail about it, which you can read later. So if you go back to the picture there, it's common sense that those guys are not there by chance. They're part of the arrangement. The chance of that happening is just phenomenal. It's much, it's 1 in a billion or something. So these two objects, objects 2 and 3, have a cosmological shift, redshift of about 0.7 equals 0.3, and the remainder must be intrinsic, presumably gravitational. Now, what happens when a consensus view is directly challenged by evidence is the evidence ignored or denied, and the challenger is discredited. Arp is a very, very good observer. He observed stuff for Hubble's theory. He was Hubble's main observer. So he got sidelined by the mainstream cosmological community. They stopped him using the big telescope. They didn't want any more of this evidence. And it's a scandal. So I'm hoping this book will rehabilitate Arp's reputation, unfortunately now posthumous, and that would make it worth writing in itself. Anyway, what I'm going to do now is to use the same inertial drag phenomenon, which was used to model rotation curves, to restore a sensible explanation for these observations and to establish a simple model for quasars with modest power output that explains all the observations. Okay, now you have to understand why consensus view is that redshift in quasars is cosmological. It comes from consideration of angular momentum. Assume that a quasar contains a large central mass, presumably a black hole, and that its energy production is due to accretion from the surrounding medium. Particles fall into the gravitational well, and the energy is released by interaction. If you've got a small but very heavy object and a particle approaching it with small tangential velocity, then it will have its tangential velocity magnified by conservation of angular momentum. And there'll be a radius of closest approach. It's like you'll get a parabola. The thing will come in. I don't know where to find a sketch pad here, but it'll come in and go whizzing around the center and go whizzing out again. It's very unlikely to actually fall in. And the same thing happens for a full flow of infalling matter from the surrounding medium. And this gives an obstruction to accretion, which was found not long after quasars discovered. And it led to the subject being dominated by the theory of accretion disks. I meant to get one of those science fiction pictures of a black hole. They always have this disk around them. That's an accretion disk. So the idea is that since falling matter can't flow smoothly into the central black hole, it must typically settle into a rotating structure of some kind, which is called, whatever its actual shape, an accretion disk. In the interaction with the infalling matter, and this structure allows energy to be produced. The consequence of this is that redshift, which is frequently observed in quasar radiation, is generally believed to be cosmological and not gravitational. Indeed, if the observed radiation comes from an accretion disk, then the redshift is caused by gravitational field from a nearby black hole, then because the disk varies in its distance from the black hole, the spectral lines will be wide, a phenomenon known as redshift gradient, not the narrow ones observed. So this in turn implies that the universe is varied. So if quasars are these huge things that then with a huge cosmological redshift, massive objects with huge power outputs, there's no observations of these close to us like these supposed near the Big Bang. So this provides strong supporting evidence to the Big Bang theory, which entails continuous change in the constitution of the universe. A steady state model cannot contain a Big Bang. And it was considerations like these that caused Fred Hoyle to abandon his continuous creation model, which is fully Copernican in both space and time, i.e., with no observable global change over time. Another casualty. Now, assume that the central mass is actually rotating and the infalling particles in the equatorial plane. Take inertial drag effects into consideration. From equation 3 above, well, I won't go back to it because it'll take ages to find it. You can read the angular momentum per unit mass as the integral of 2 omega r dr plus a constant. That's the apparent angular momentum from the distance, and the true angular momentum, you want to pop off you want to replace v by v inert, and you get this formula here in the box. Now, you've got an integration constant there, so there are solutions with low angular momentum, either true or apparent, for r small, and a significant angular momentum, the larger r. So you've got the angular momentum that's further out is being absorbed by the black hole, by the inertial drag effect in the black hole. So what it means is effectively that a rotating body can absorb angular momentum. And this holds for almost any dynamical theory, in particular for general relativity, and for almost any non-trivial function omega. It's just a relativistic effect. You get the feeling that cosmologists do not believe in relativity. They never use subtle relativistic effects. They typically use linear approximations to relativity. Very interesting. I mean, Einstein was just as bad as the rest of them. He stuck with what is essentially a Newtonian model with relativistic bits. Anyway, if angular momentum can be nullified by central rotation, it does not force the existence of an accretion disk, and you can have a simple spherically symmetrical model where accretion can be used. So here's another description which gives you further information. The formula for omega, equation 1, implies, that's back there somewhere, implies that the inertial frames near the origin rotate at roughly the same rate. In other words, all fit with plate-like rotation. If the speed of this rotation is the same as the effective rotation of infalling matter, then the latter rotation will be rotational due to the rotation of the inertial frame and not inertial. Conservation of an angular momentum which acts only on the inertial velocity will not change it, and the radial and the inflow will be radial in the local inertial frame. So there's a feedback effect working in favor of this. If the incoming matter has excess angular momentum, then it will tend to contribute to the central rotation, which therefore changes to increase the inertial drag effect until the two balance again. Conversely, if there's a shortfall, the black hole will slow down. In other words, once locked onto the ambient conditions that allow the black hole to accrete, there's a mechanism for maintaining that state. Short digression is needed here. In order to apply Sciama's principle to black holes, it's necessary to assume the black hole has a well-defined angular velocity as well as a well-defined angular momentum. In other words, the black hole has an effective radius, RF, related to angular momentum by omega equals m omega, little omega, capital omega equals m little omega RF squared. So for black holes, which are fictitious objects because we've never actually seen one, the fiction is that the actual radius is 0, total gravitational collapse, and hence angular velocity is not determined. So it's a singularity. There aren't any singularities in the universe. So this assumption is equivalent to replacing conventional theory, my assumption, conventional theory by the more sensible assumption that in the collapse to a black hole, matter reaches a small but non-zero size. Since RF is small change in angle, let's go back to this formula there. Since this is small, a small change in angular momentum is quite a large change in the angular velocity, so that you can get speeding up and slowing down very quickly. So this makes the locking on effect I've just described more responsive and effective. If incoming matter has angular momentum at a different axis, then a similar feedback effect causes the black hole rotation axis to change into alignment with axis. So kind of the black holes fit. They learn how to accrete, how to grow, how to feed in a rotating environment. Okay, so the conclusion of this is the angular momentum instruction for accretion can be ignored, and a spherically symmetric accretion model can be used. And a suitable model is based on the Schwarzschild metric. It's studied in joint work with Robert Mackay, I've mentioned before, and our student Rosenberg Toala Enriquez, who was a student a few years ago now. It's been going on so long. In this model, gravitational redshift can take arbitrary values. So this is a formula from our model for the gravitational redshift for a black hole accreting. So Z is 1.27 times 10 to the 7 masses. Mass in solar masses. Now this is I'm not using natural units, I'm using MKS. So M is the black hole mass in solar masses, N is the density of the ambient gas, which is number of particles per cubic meter. You assume you're in a hydrogen gas, hydrogen atoms or protons, depending on on whether it's polarized, whether it's whatever it is, whether it's a plasma or not. And T is the temperature in degree constant. X is an absorption factor, which can be taken to be a half. In other words, you just ignore the factor in square brackets. I changed it in this print. It's gone. It's still there. So the full details of the model, which I call the three-author model, are given in the appendix to the book, so you can pick that up and look at it afterwards. But there's a very important point about this equation. Z something times mass inverse times something else. So the mass of the black hole appears inverted. So other things being equal, redshift decreases with black hole mass. Now, ARP actually observed this. He observed that the redshift decreases with black hole mass. The black holes start out small with a big redshift, and as they grow and get bigger, the redshift decreases. Now, ARP didn't have any of the theory that I've got here, and so he invented some fantasy physics to explain it. And this is one of the reasons why he's partly considered a nutter. But anyway, there's nothing wrong with his observations, and he's a fantastic observer. And it's a real shame that he was drummed out of the thing. Okay, sorry, that's it. That's the end of Quasars.